Okay, so we talked at the beginning when we started talking about op amps, we said that op amps were used for various things. Now, we looked at them as just little plain linear amplifiers. But op amps have other purposes, and we talked about how we use them for mathematical operations. We use them to make decisions. They are essentially, they were, or still are, analog computers. They can actually look at signals, make a decision, render an output that we can use. Before we had computers, well, we used a lot of op amps, and we could do different things with op amps. We could sum voltages, we could do integration, we could do differentiation, and we could also do comparisons. So comparisons are pretty cool. One of the little devices we're going to look at probably later on is like a 555 timer. They have comparators in them, and they kind of make a decision. So we'll take a look at this first one. This is a very simple one that we can build with an op amp. Just to let you know, when you are using comparators, there are packages that are specifically made just for doing comparisons. So you can buy like an op amp comparator that's its only job. That's what it's designed for. It doesn't mean you can't use an op amp to do it, but there are slicker packages around that will permit you to have better results. But this will work. So we'll start off by looking at this thing, and you'll notice in this case there is no negative feedback. This amplifier works basically using its open loop gain. So whatever's at the inputs, which is going to be a lot more than just a couple of microvolts, is going to be amplified at the output. So it's very important that I also indicate what the power supply would be to this thing. So I'm going to put, in this case, plus 15, negative 15. So the output of this thing, ideally, can be only one of two things. I can have an output of plus 15 or negative 15 at the output. It'll either saturate or cut off. If the supply rails were 8 volts and negative 8 volts, well, the output could only be plus 8, negative 8. Okay, it's based on the voltage supply. Now, in real life, if you go measure, if you're using plus 15, minus 15, you might find that 14.8 and negative 14.8. There's a little bit of losses, but for analysis sake, let's just stick with the power supplies, and we'll forget about the losses. So the output can only go high or low. So this thing, this op amp, this comparator is going to give you a decision. Yes or no. On, off, plus 15, negative 15. Okay, so that's the only two possible outputs. Because basically what it's doing is taking the difference in voltage, multiplying it by the open loop gain, and it can only saturate or cut off. Okay? So now there's this voltage right over here, which we're going to refer to as our reference voltage. So voltage that's right at this point is V reference. It's our reference. Or we could actually say it's our threshold. So it's a threshold voltage. And again, we've got 10 volts here. And a voltage divider with 2 equal resistors going to ground. So the threshold voltage would be, well, 10K, 10K. This would be 5 volts. So that's going to be our switching point. It's going to be this 5 volts that we've got on the other input. So what I'm going to do is I'm going to draw a little dotted line here, right down the middle, my input signal. So my input signal, what I'm giving it is I'm giving a sawtooth wave, a triangular wave, that is ramping from 0 to 10 volts and 10 back down to 0. It goes up and down like that. And right down the middle, a little line here is where we've got our 5 volts. So my little timing diagram over here, I'm just going to indicate it's 5 volts. So based on that information, I can determine what the out would be. So I'm just going to draw some lines here. So on and so forth. So the way this comparator works is very simple. Whenever the input voltage is below the threshold. So if I've got a voltage below 5 volts, well, this input is higher than this, so that means the output would be negative. So right over here, while my signal is below 5 volts, this one's higher, so V out right over here starts off at negative 15. When the voltage at the input is higher than the reference, well, the output switches to plus 15. Then switches back down to negative 15, and plus 15, negative 15. So that's basically how the comparator works. It compares the two voltages. So in this case, when your input voltage is lower than your reference, your output switches to negative 15. Whenever it's higher, switches to plus 15. And what you could do by playing around with this voltage divider, you can move that reference anywhere you want in there. You can make it 1 volt to 2 volts. So for instance, if you had a sensor and you determined that whenever voltage coming off the sensor is greater than 1 volt, turn off the relay. So you could use this signal here to switch a relay on or off. You could start a pump or start a heater or shut off a heater. You can do whatever you want with that. Okay, so that's what the comparator basically does, is it compares its reference voltage to whatever's coming in and makes a decision. So that's pretty easy to understand what's going on there. In a 555 timer, for instance, the timer works on the principle of charging and discharging a capacitor. So what we do is we slowly charge up a capacitor. When the voltage on a capacitor gets to a certain level, the output switches. So we can get a square wave, and then when the capacitor discharges, then the output falls back down. So our timer, we can play around with the timing constant, okay, the RC constant on our capacitor resistor pair, and change the timing of our 555 timer. You'll see what I mean when I give you one to play with, but we can use the charging, discharging a capacitor to create a timer. All right, and inside of that little chip you're going to have, it's 055, there's a couple of comparators, and that's what they do. They watch a capacitor, and when the capacitor hits a certain voltage, bang, they turn on the output. And then when it falls below, they turn it off. Okay, so that's your basic comparator. Now this is a very, very simple comparator, and it's got a couple of little problems. It's got one little problem in particular. Again, we're going back to our big boogeyman, noise. What if we've got the signal coming in and there's noise on it? So the noise would be riding on top over here. Do it in blue here. So if I had some noise sitting on top of here, so there's a bit of noise there. Oh, ouch, ouch. It goes, oh, ouch. Ouch. It always hurts when it goes through the reference point, okay? So if you go right over here, right, these points, there's a switching point right there. Now here's the problem. If you've got noise, a lot of noise, at these points where we're switching across, well, there's the very, very distinct possibility that the output over here, before it goes from, we'd like it to go negative 15 to plus 15 and stay there, but what it's going to do is it's going to glitch. It's going to go up and down a few times until it settles. Then we'll do the same thing up and down a few times until it's messy. So if you had a relay on there, you'd hear the relay whenever it goes through the switching points because of the noise. You hear click, 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 and then it would settle. And then it goes back there, click, click, click. So noise causes problems, causes glitching at the output. Is that right? So that's one of, so we've got to figure out a way to kind of get around that problem. There's got to be something. So what we're going to do is we're going to introduce another comparator called a window comparator. So do a little window comparator. So I'm going to draw a little circle like this here, up, and up, and watch carefully. This is not an amplifier. This is not an amplifier. This is not an amplifier. I'm going to have my input here, and I'm going to make my input go from negative 10 volts to positive 10 volts. All right. Again, my power supply Oh, and let me put some resistor values here. So I'm going to put 10K. Then I'm going to put something like 1.8K here. And in my power supply, I'm going to put, let's see, plus 15, negative 15. So you just heard me saying this is not an amplifier. This is not an amplifier. This is not an amplifier. Why? If I look at that, it's, you know, a lot of people would look at that on a test and they're going to say, hey, that looks just like a non-inverting configuration. But there's a telltale sign on there. So there's something on there that says, no, it's not. That's not an amplifier. Why is that? Why is it not an amplifier?
Because you got your input. It's negative feedback.
Huh? No negative feedback, exactly. It has to do with this sign right over here. You see this is positive feedback. That doesn't work. Okay, positive feedback creates a snowball. It's like that snowball going like it's gonna. So the output is going to saturate. It's either going to be plus 15 or negative 15. There's no way for this thing doesn't amplify. This is positive feedback. This is the key right here. If the feedback doesn't go to the negative and it goes to the positive, you know this ain't an amplifier. Well, there's an amplifier there, but it's just not going to work as a nice linear amplifier. Okay? So watch where that feedback's going. It's going to tell you the difference between whether this thing is a comparator or a nice linear non-inverting amplifier. Okay? Positive feedback. Not so good. Okay. So you guys won't get caught that way. Now we're going to go look at, right over here, we're going to go determine what our reference voltage is, our thresholds. There's two of them now, and I'll tell you why. So you will notice here that I have V out. V out can be one of two things. It could be plus 15 or negative 15. It's going to be one of two states. Which means that V reference, which is in the middle of our voltage divider, can have two values now. It all depends. If you've got plus 15, well, you're going to have a positive reference voltage. If you've got negative 15, well, current changes direction, you're going to have a negative reference voltage. So let's figure out what that reference voltage would be. So Vref is going to be equal to plus minus 15 times, well, we've got a voltage divider here, so it's going to be the voltage falling on this resistor over here, so it's going to be times 1.8K over 11.8K, which is the sum of both resistors, right? So if you want a voltage on one resistor, you go that one resistor divided by the sum of both. So it's going to give me, so 1.8K over 11.8K times 15 volts plus or minus will give me the reference voltage. You guys figure that out for me.
Minus 2.28.
Plus or minus 2.28 volts. So this reference voltage plus minus 2.28 volts. Ah, okay. So I guess the next thing to do is let's make a timing diagram and see what happens. So here. Alright, so here I'm going to put V in. I'm going to put my sawtooth wave here. Okay, And I've got mine going from -10 to +10. And here's what I'm going to do is I'm going to put my two, so down the middle is 0. So I'm going to put my two reference voltages. So I'm going to put a dotted line, red one, the top one. So dot. And that's going to be 2.28 volts. And then I'm going to put the other one, which is right underneath. Like that. -2.28 volts. That's the other one. It's all right. And underneath, we're going to have V out. V out. And I'm just going to put a timer here. We'll call this right at the beginning here. We'll do 0 seconds. 0 seconds. So we start off. All right. Now, you'll notice we've got these two thresholds. All right. That's what they call, that's the window right there. This is the window. That's the window we talked about when we call that a window comparator. And that little ditty of a window, also we could refer to that as hysteresis. So we've got hysteresis there. Very interesting. So we're going to start off at 0 seconds. So at 0 seconds here we go. We've got a very low voltage over here. All right. And low voltage. Chances are, if that input is really low, it's going to be like that. Then it's going to be higher. Oh, we'll have plus 15 at the output. So we'll start off with plus 15. So our voltage will start off at plus 15. So since we're starting off at plus 15, we know that our reference point that's going to be available to us is going to be this one right over here. All right? So the switching is going to occur. So when the input rises about right at this point, so we're going to plus 15, all of a sudden the output is going to drop, bang, to negative 15 volts. And then what's going to happen is the reference voltage is going to switch over to the negative 2.28. As soon as we cross over, as soon as this signal comes over and hits this point, voltage falls to negative 15. All right? And the switching point switches now to over here. Negative 2.28. The output's negative. So the output continues over here. And when the signal drops below the negative 2.28, up it goes. And guess what? So there's the reference point, the switching point. It flies over here. So stuff doesn't change until it hits this point over here. And when it hits that point over there, bang, it switches back. See what's going on here? So every time the output switches, the reference point, the threshold, switches over. Now, why would we do something that sinister? Well, here's the reason. Let's say we've got noise on the wave. So let's say I've got this noise. So I've got a bit of noise on here. Noise. When it hits the switching point, it goes over. What if it comes down below the switch? Oh, wait a second. If it comes down below, the switching point isn't there anymore. The switching point is over here. So the noise would have to be so great that it would have to come down here to cause switching again. So by having a window, the minute you cross over your reference point, the reference point moves away. So that if the noise causes the signal to come down, it can't cause any glitching on the output because it would have to have so much noise, it would have to cross the other switching point. Everybody get it? So the idea is when you've got noise, what you do is you play around, you make a window, and the wider the window, the more noise immunity you have. Isn't that cool? And that's how a window comparator works. So what you do to play around with the size of your window is you can play around with the ratio of these resistors and size the window any size you want. If you've got a lot of noise, wider window. Less noise, smaller window. And not only can you do that, if you play around with the voltage down here, like I put it to ground, but if I had a voltage here, a variable voltage, I could move that window up and down anywhere I want it. Ta-da, window comparator. That's how that works.